When we talk about electromagnetism induction, we'll think of the Faraday's law. We have the first law: whenever a conductor cuts a magnetic flux, an EMF is induced in the conductor. Second law: the magnitude of the induced EMF is equal to the rate of change of flux linkages. So we put in equation. Suppose a coil has an N turns and flux through it changes from an initial value of phi 1 Webers to the final value of phi 2 Webers in a time t second. The initial flux linkages we assume is n phi 1. Then the final flux linkages will be n phi 2. So there's a changes within that time period. Then we put it in this equation, it will be induced EMF. So E equals to, we factorize, equals to d phi over dt. d phi means the difference of the phi 2 minus phi 1. dt is the difference of the time. So this is the equation of the Faraday's first law and second law. And then where's the direction of the induced EMF? We use Fleming right hand rules. So if the fingers on the right hand rules is pointed in the direction of the magnetic flux, thumb is pointed in the direction of the motion of the conductor relative to the magnetic field. The second finger represents the direction of the EMF. So Fleming right hand rules. This is our magnetic flux field. This is our velocity of the conductor. So if let's say the conductor is moving 90 degrees perpendicular to the magnetic flux, then this is our current induced. The induced current will be equivalent to the induced of the EMF. So for example, if a wire with the proper orientation moves through the magnetic flux field, a voltage is induced in it. The idea is shown in the figure 1, this one. So B magnetic flux is going through this paper, and then the conductor is moving to the right side. So the current will flow through upwards. So when current flowing through upwards, it is actually a battery, which means when we connect this one to a resistor, so the current will go through to this direction, right? So when current go through this direction, this will be our positive polarity. This will be our negative polarity. And then we will put in the equation where E induced equals to V cross B, the velocity cross the magnetic flux density, and then dot the length of the conductor. Three of them are vector. So we can put in this way. E induced equals to V times B sine theta, then times L cos alpha. For example, figure 1.7 shows a conductor moving with a velocity of 5 meters per second to the right of the presence of a magnetic field. So this is the magnetic field, and then this conductor is moving to the right. The flux density is 0.5 Tesla. This one B is 0.5 Tesla into the page. So into the page, we will see the tail, cross tail of the arrow, and the wire is 1 meter long. What are the magnitude and the polarity of the resulting induced voltage? So we want to find the induced voltage. We use the equation VB sin 90 times L cos 0. So VBL. V is a 5, B is a 0.5, L is 1. Then it is 2.5 volt. Positive at the top of the wire. Then another guy is saying that the Lenz's law. The direction of the induced EMF is always such that it tends to set up an current, opposing the motion or the change of the flux responsible for inducing that EMF. So just now we have a E induced equals to N d phi dt, and then Lenz found that actually we need to put another one is a negative here. It shows that the induced EMF always need to generate to oppose the change of the flux. So for example, if this situation where the north pole create the flux of B, suddenly it move in. Okay, so when it move in, the flux will increase by changing in this direction. And then the Lenz's law saying that the coil must be created, the induced EMF, where it will oppose the changes. So now we want to create the in order to create the opposing induced magnetic flux density, where is the direction of the current need to induce here? So we use right hand rules, going like this. So we know that going like this, going like this, so the current will flowing downwards like this, so that it will create the magnetic flux, this one, magnetic field in this direction to oppose the changes here. So what if when the pole need to go out from here? So the original, the flux is in here, in this line. So if let's say the magnet is moving outwards, which means there's a changes of the magnetic flux density. And then, according to the Lenz's law, this circuit need to create the magnetic flux that can oppose these changes. So how to create is we use a right hand rules, okay, like this. We will create a magnetic in this way to the left, okay, so that to oppose the changes. This is Lenz's law. Same happened to the south pole, okay, I mean in this scenario. So for example, now I have a flux going topwards, going to the top, okay, and then we need to know where is the direction of the induced EMF or the current. So very easily, I need to create the induced EMF need to create so that it will oppose the flux here. So how to create the flux oppose here? Okay, we will create like this one, okay, where the current will go to like this way. This is called direction of the induced EMF. So the line of the force in the magnetic field are called magnetic flux. This is called field lines. Then this is a magnetic flux. And the general direction for the magnetic flux flow is from north to the south. Phi from the north to the south. And then the symbol is a phi. Unit is a Weber. So flux density is defined as a flux per unit area. Phi divided by A. Called B. Now B is under Tesla. The unit is Tesla. Phi is Weber. A is meter square. And then the strength of the magnetic field is measured by the flux density. So how good is the strength? Then we use a flux density to define. Or it is measure how many fields lie in a certain area. So there's a stronger field at the poles where there are more field lines. So for example, more field lines here. This is stronger field. Less field line here. This is not strong. Okay. Then a magnetic field is often called as a B field, and then the symbol will be B, unit will be Weber per meter square or Tesla. So for example, for the coil in the figure below, determine the flux B in the Tesla. So B is the phi divided by A. So phi is a 6 times 10 to the power minus 5. A is a 1.2 times 10 to the power minus 3. So B equals to phi over A. 6 times 10 to the power minus 5 divided by 1.2 times 10 to the power minus 3. So we have a 0.05 Tesla. Then another one is a permeability. What is permeability? Permeability is the ability. It is used to describe the ability of the magnetic material or the ability of the material that produces the flux in the magnetic circuit with a magnetization force. Or we can say that the ability of the material for the flux to flow through the material. This is called permeability. Which means if they say the material can allow a lot of fluxes flowing through it, then the value will be greater, will be higher. So the material is said to have a high permeability when more fluxes can flow through it. And we use a symbol of the mu, and unit will be Weber per ampere meter. There are three types of permeability. One is permeability of the material, mu. One is the permeability of the free space. Free space means vacuum, mu naught. And then it is a 4 pi times to the power minus 7 Weber per ampere meter. Relative permeability, mu r, the third one, is the ratio of the permeability material, this one, divided by permeability of the free space. To related three of them. So we can put it in this equation. Or mu equals to mu r times mu naught. Then ferromagnetic materials have a very high level of permeability. The material where it has a ferromagnetic. Ferromagnetic means ferro is iron. Magnetic means got the magnetic characteristic. So the iron with magnetic characteristic. has a very high level of permeability. So we have a non-magnetic material, for example, copper, aluminum, wood, glass, and air. It's the same as a free space. So we have by using this equation, ferromagnetic material mu r is more than 100. Non-ferromagnetic mu r is equals to 1. When mu r is equals to 1, mu equals to mu naught. What is mu naught? Mu naught is the permeability of the free space or vacuum. So another one is reluctant. Reluctant is the resistance to flow of a magnetic flux. In electric circuit, we have resistance, right? It used to resist the current. In magnetic circuit, we have reluctance. It used to resist the flow of the magnetic flux. Okay, we can put it in this equation. R equals to L over mu A. L is the length, mu is the permeability of the material, A is the area. So by applying the Ohm's law for magnetic circuit, we have F equals to phi R, or phi equals to F divided by R. Phi is magnetic flux Weber, F is magnetomotive force, ampere turns. R is reluctant, ampere turns per Weber. So magnetomotive force, MMF, F, is proportional to the product of the number of turns around the core and the current through the turns of the wire. We put it in this equation. F equals to Ni. So N is turns, I is ampere. So F equals to ampere turns. The unit is ampere turns. Yeah. So according to the Ohm's law, if let's say we put in electrical circuit, we have the voltage, we have the resistance, we have the current. This is the circuit. Then we put it as a V equals to IR. Voltage, yeah, actually we are talking about electromotive force. The force created by electric. Then, if let's say the Ohm's law in the magnetic circuit, we have the this so-called the coil, and then we create the flux flowing through the material. So this is the coil that produces the magnetomotive force. You see, electromotive force is actually in electric circuit. Magnetomotive force is due to magnetic. Okay, so it will create the flux we call magnetic flux, and then flowing into the reluctance. So in electric circuit we have V equals to IR. In magnetic circuit we have F equals to phi R. Well, the magnetomotive force per unit length is called magnetic field intensity. H equals to F over L. Well, another new equation, ampere turns per meter. Magnetic field intensity H is determined solely by the number of turns N and the current I and the length of the core L. So H equals to Ni over L. We also have the flux density and the magnetic field intensity are related by the equation where B equals to mu H. So there's a lot of equation, right? So I put it in a summary. First of all, we need to look at the green labeling first. We will start from F equals to IR or V equals to IR. F equals to phi R, or similarly in electrical circuit V equals to IR, right? Then we go further. So first A finish, we go to B. We go to C, the left hand side first. F actually equals to Ni, also actually equals to HL. Done B, then we go C. Phi equals to B times A. Then B, we know that B equals to mu H. Mu equals to mu R, mu naught. So done. Fine. Then R actually equals to L over mu A. Okay, so this is all the equation that we need to memorize and how it comes out. So then another problem is, what about the units? It's very confusing, right? So we'll go to the lowest level first. So see at the number 1, N is actually turns, I actually is ampere. So we have a turns with an ampere. Number 3, this is the L in meter. Then we need to find the H. H actually is a turns times ampere divided by M. So ampere turns divided by M, or we call it as ampere meter minus 1. Okay, 1, 2, 3, 4. Then we'll go back to F, 5. So what is the unit of F? F actually is turns times ampere. So we have ampere turns. Then we go to 5, 6. Okay, this one is already fixed. It is in Weber. Then we go to 7. Pi equals to BA. B also fixed in Tesla. Then we have meter, area in meter square. This is 8. Then we go to 9. We need to know the mu naught. Mu naught also fixed. It is under Henry per meter. Okay. Then we know that mu r, number 10. Mu r is dimensionless. Dimensionless means it is a ratio. There's no unit. Okay. 10. Number 11. Since this is dimensionless, so this one times this one, it becomes the same, which is Henry per meter. Or we can find this unit from here. B, we know that it is Weber divided by meter square. And then H actually is ampere per meter. So we can get this value. Or usually we just use H per meter square per meter. Then after that we have 5. So 9, 10, 11, then we go to 12. So what is the angle, what is the unit for the reluctance? So we come from here. Reluctance actually F divided by 5. Ampere turns divided by Weber. Ampere turns divided by Weber. So this is all the brief summary for all equations. Remember, when it comes to solve this type of equation, we must list out of the equation first. Okay? So for example, we want to find the value of I needed. Then we have a magnetic flux of 4 times 10 to the power minus 5. We have the permeability of the material. We have the N. We have the ampere. So we want to find the I. How? So first we find the B first. Phi given value, we have ampere. Then we find the B. Then when we have the B, we have the mu. We can find our H. After that, we have H. We have L. We have N. We want to find our I. Okay. So Ampere circuit law. Ampere circuit law is quite similar to the Kirchhoff voltage law and the current law. So Ampere circuit law state that the algebraic sum of the rises and drops of the MMF around a closed loop of a magnetic circuit is equal to 0. So total F will be equal to 0. So which means when we generate the magnetic flux that flow through in the steel, all the source to the magnetic circuit reluctant component will be sum up become 0. Okay? And then we also can apply the formula F equals to HL or F equals to 5R. Okay? Now for example, and we know that this coil generated the MMF will flow through inside this material. So we have 3 materials. One is iron, one is steel, one is cobalt. So when there's a different material, there will have a different MMF. And then according to the Ampere circuit law, total F will be equal to 0. So this is the source. N times I will be the source. Okay, N times I will be the source, and it will be distributed in this area, and this area. So, well, source will be equals to total. So, source equals to HAB times LAB. HAB is like this. Okay, HAB times LAB. Plus HBC times LBC. Plus HCA times LCA. Okay. So also the same. The sum of the fluxes entering a junction is equal to the sum of the fluxes leaving a junction. So let's say I have a junction A and junction B. The phi going to the junction A will flow out from junction B and C, flux B and flux C. So flux A go in, flux B and C go out. In, out, out. Then in, out. So in, out. Okay? So as combination, series and parallel magnetic circuit. So for example, in this case, we have a source here. MMF created the source here. Then we have a 1 reluctant, 2 reluctant, 3 reluctant. So we have a 5, 5, 5. So put it in a magnetic circuit. We have a source. So I have a reluctant 1. I have reluctant 2 is here. This is reluctant number 2. I have a reluctance number 3 here, so I put it in here. Then I assume this is a loop number 1. I assume this is loop number 2. Then I have a phi 1, phi 2, phi 3. So what I need to do is I create an equation, several equations. So Kirchhoff's law, phi 3 in will become out, out. So phi 3 equals to phi 1 plus phi 2. Phi 3 go in, phi 1 go out, phi 2 go out. Then loop 1, the source will distribute to these two reluctants. So N1 equals to H3L3 plus H1L1. Same as well, loop number 2, the source will H3L3, H2L2. It is exactly the same as the Kirchhoff voltage law. Actually, I need to put a plus minus here, okay. Then another one is the source here. I have reluctant, 1 reluctant here, 2 reluctant here, 3 reluctant here. So source here, 1 reluctant, 2 reluctant, 3 reluctant. I create the loop. I put the flow, the direction of the fluxes. So 1 in, 2 out, 1 in, 2 out. Source, for this loop, source distribute these two. So N1 equals to H1 I1 plus H3 I3. Then this one actually, because I have a plus minus here, so H3 L3 equals to H2 L2. Actually, there's a plus minus. There's no sign here. We need to put the plus minus here. Same goes to with the air gap. When there's an air gap, it will be air gap reluctant. Okay. That one is just for your introduction. So ideal transformer efficiency. We'll talk about ideal transformer efficiency, and the current transformer. So ideal transformer means there's no lossless. All the energy induced here will go to the other side. So we call this one as a primary side. This is secondary side. When primary side, we have a primary winding. Secondary side, we have a secondary winding. The primary side will have a primary voltage. So V1 equals to N1 d phi dt. This is from primary side. This is the symbols. Okay. Then for the secondary side, all the induced voltage will go to, all the induced fluxes will flow to the secondary side. So we have a V2 equals to N2 d phi dt. And then we use V2 divided by V1, N2 divided by N1. Then this one will be the same. So I deduct it. I have this equation. Then we found that it is a transformer ratio. We call it as a turns ratio. So summary, V2 divided by V1 equals to N2 divided by N1 equals to N, which is a turns ratio. Then, since the transformer is ideal, there's no losses in the transformer. So the efficiency of the transformer must be 1. Efficiency is P out divided by P in. P out the same with the P in. So N is 1. Our efficiency is 1. So, or we can put it in the, since it is efficiency is 1 or lossless, the power input was same as the power output. Power input is V1 I1. Power output is V2 I2. Then we'll have I1 divided by I2, V2 divided by V1 equals to N. We found it from the previous slide, right? V2 divided by Vn is N. V2 divided by V1 is N, which is I1 divided by I2. So if I put I2 at the top, I1 at the bottom, then it will become N2 divided by N1 divided by N2, which is 1 over N. You can try to see the relationship from here. Okay? And step down transformer is one whose secondary voltage is less than the primary voltage. For example, I have a 1000 volt in the primary side. I want to get 100 volt in the secondary side. This is step down. I can have a step up as well. If let's say I have 100 volt in the primary side, I want to get 2000 at the secondary side. Also can. We call as a step up transformer. For example, in an ideal transformer is rated as 2400 volt to 120 volt with a power of 9.6 volt ampere, has a 50 turns of secondary side. We want to find the turns ratio. We also want to find the primary, the turns on the primary side. So what is the equation that we need to use? So we know that this is primary side, this is secondary side, and equals to V2 divided by Vn, where V2 is the secondary side, 120 divided by 2400, which is 0.05. Then we know that we want to find the N1. So we use N equals to N2 divided by N1. We have a N2 which is given 50. We have an N calculated 0.5. Can we find N1? Yes, N1, then we find it. Another one. Usually we use the transformer in the instruments transformer. Instruments transformer are designed to perform the specific measurement. Actually, they used to do the measurement. So the one of it is a very famous one, is a current transformer. It is designed to measure the current in line without breaking the line to insert the meter in series with the conduction path. Usually when we want to measure the current, what we need to do is we need to cut off the circuit. Then we plug our measurement instruments in series with the magnetic circuit to measure the current. But when we want to measure high current, that will be a problem. So what we need to do is we need to have a current transformer. Okay? So due to the high current and voltages encountered in a high power distribution system, the use of a current transformer is a welcome option from a safety viewpoint. So this is the typical current transformer. For example, this is the high tension windings, phases, transmission line. So we can couple a current transformer here. It will step up the primary to secondary. Then this is the typical commercial unit. So thank you very much. Hope you enjoy the slides.